Hello everyone, I am Poulomi from Colorado School of Mines. Today I will be talking about our work, Givenness Hierarchy, Theoretic Cognitive Status Filtering. Before moving on to our work, let us consider an example scenario where a human asks a service robot of a building about the IT help desk, and the robot answers back saying it is on the second floor. This simple dialogue requires the robot to refer to a location in the building. To do so efficiently, the robot must determine how best to refer to the location, that is, deciding whether to use a full description like the IT help desk or a more concise form like it. One of the most established theories of reference Gundl's Givenness hierarchy, as shown in the image, consists of a nested hierarchy of 6 tiers of cognitive statuses, each of which is associated with a set of referring forms that can be used when referring to an entity with that status. Accordingly, a speaker's selection of a referring form depends on their assumptions as to the cognitive status of their target referent in the mind of their conversational partner. Similarly, Gundl's Givenness hierarchy coding protocol provides guidelines as to what features of linguistic and environmental context should dictate the cognitive status of a given entity. For example, this protocol suggests that an entity that is mentioned in a topic role in the preceding clause should be considered to be in focus. Previously, researchers like Williams and his peers had presented the full computational implementation of the Givenness hierarchy using a set of handcrafted rules informed by the Givenness hierarchy literature. However, that approach was designed specifically for robotic natural language understanding, oriented around Givenness hierarchy-inspired memory structures used to assess what entities are candidate referents given a particular cognitive status. In the previous example, when the robot says it is on the second floor, it is traditionally associated with the cognitive status in focus. So from the understanding side, the human can look into the set of things that are currently in focus, which is the IT help desk. Thus, the person is going to assume that the robot is probably talking about the IT help desk. In contrast, natural language generation requires a model in which cognitive status can be assessed for a given entity. Thus, having data structures associated with cognitive statuses does not really work for natural language generation, because for natural language generation, we already know what thing we are going to refer to. And the question is, how should we refer to it? So we do not need to search for anything we already have the representation for, though all these data structures in order to figure out which data structure contains the thing, as this would be inefficient. So instead, for the purpose of natural language generation, we wanted to directly associate this representation with that cognitive status, which brings us to the question, what is the best way to model this direct relationship between a particular entity that we are tracking because we think it is going to be relevant to the conversation and the status it has, so that we can figure out what the best way to refer to it is. Such a model of cognitive status could either be developed as a rule-based model or could instead be developed as a statistical model which would attempt to learn to predict an entity's cognitive status from the data. Thus, we propose and compare two models of cognitive status, a rule-based finite state machine model inspired by the Givenness hierarchy literature and a statistical data-driven cognitive status filter model. We formulate the cognitive status modeling as a Bayesian filtering problem given by the equation here. Considering a dialogue that consists of a set of utterances for object O, let S denote the cognitive status, either in focus or activated or familiar, at a particular time step t for a particular utterance. And let L denote the linguistic status, either not mentioned or mentioned in a topic role or mentioned in a non-topic role of object O in the utterance. Using this formalism, our goal is to recursively estimate for a given object the probability distribution over cognitive statuses for object O at time t. We define a Bayesian filter of this form as a cognitive status filter for a given object O. Accordingly, for our problem formulation, we make these simple assumptions. For cognitive status information, we assume that all objects have a status of at least uniquely identifiable or higher. We also consider each object to be either in focus or activated or familiar. Thus, if an object is not familiar, we exclude that entry from our model. Similarly, for linguistic information, we consider only 3 notions of linguistic status to keep our model simple. The data set that we used is the OFAI Multimodal Task Description Corpus that is originally in German but translated to Silver Standard English for our work. The dataset consists of human-human and human-robot dyads revolving around 4 different tasks. But for our purpose, we used only task 3 as shown in the image here that consists of 16 monologues. To collect linguistic status information L, 3 annotators independently annotated the OFAI multitask description corpus, that is all the 16 monologues from task 3. As a first step in this work, we begin by using a small subset of the original dataset consisting of 4 monologues, each of which consists of 4 utterances to control for monologue length. Here is an example monologue that we used in our experiment. U1 to U4 represent the 4 consecutive utterances. Ground truth cognitive status information was then collected through a crowdsourced human subject experiment. 160 US participants were recruited from Amazon Mechanical Turk. 2 participants answered an attention check question incorrectly and were dropped, leaving 158 participants for our data analysis. At the beginning of the experiment, each participant was shown the scene of task 3 and instructed to remember the objects and their labelings. Participants were then shown the same scene without labels while listening to a portion of one of the experiment's 4 monologues, as read by the experimenter. At the end of this monologue excerpt, participants were asked to answer 2 randomly ordered questions. One question asks them to click on the object in the scene that they thought the speaker would most likely be referring to if the speaker would have said, "Look at it" at the end of the monologue, depicted here by question Q1. And the other question asks them to click on all the objects in the scene that they thought the speaker would most likely be referring to if the speaker would have said, "Look at that" at the end of the monologue, depicted here by question Q2. These questions allowed us to examine the user's implicit beliefs as to the cognitive status of the objects in the scene. From a Givenness hierarchy theoretic perspective, if a participant implicitly believed a given object to be in focus, they should click on that particular object for both the questions Q1 and Q2. Whereas if they believed the object to be activated, they should click on that object for question Q2, but not for question Q1. Thus, if a participant believed the object to be familiar or lower, they should not click on the object at all. Using this coding procedure, we are thus able to determine the perceived cognitive status of each object in the scene for each participant after the completion of the monologue excerpt they were exposed to. When paired with the linguistic status annotations, this allowed us to train our CSF model. Our CSF model was trained by calculating the conditional probability table given by the component shown here. To evaluate our CSF model, we considered each object O and each monologue M and retrained our model using all data except that which was collected for object O or monologue M. For example, while testing for object O1 in monologue M1, we retrained our model with all the data except that concerned with M1 and or O1. We used this model along with a prior distribution over cognitive statuses for that object to simulate what status would be predicted for that object at each point in that monologue. U model referred to an uninformed prior probability of 0.33 each, whereas the I model referred to a weakly informed prior probabilities of cognitive statuses as mentioned here. These probabilities reflect the fact that these objects are a priori far more likely to be familiar than activated, and among the set of things that are currently activated, it is more likely for a given object to be activated than in focus. We evaluated the model's prediction by comparing it to the majority opinion from participants who had provided data for that object at that point in that monologue. Combining these prediction results for all 8 objects in all 4 utterances in all 4 monologues produced a 128 element prediction vector for the model. In addition to our CSF model, we also computed the prediction vectors for 2 baseline models. First, we computed the decisions made by a rule-based finite state machine model, which formalized a set of heuristics from the Givenness hierarchy coding protocol. The states here correspond to cognitive statuses, and transitions are triggered based on linguistic statuses observed in incoming utterances. Second, we computed the decisions made by a random baseline model, which predicted cognitive statuses at random. The overall results comprises the accuracy measurement of each model following with a McNemar's test for pairwise model comparisons. The overall accuracy of each model is shown in the bar graph here. Our U model had the highest accuracy, and our I model and the theoretical FSM model had the same accuracy, slightly less than the U model. The accuracy measure of the FSM model suggests that the heuristics encoded in the Givenness hierarchy coding protocol are a good representation of the patterns that can be learned from the data we collected, given our choice of data annotations. The similarity of the CSF model's accuracy to that of the FSM similarly demonstrates that the CSF did a good job of automatically learning these patterns from our data. The slightly higher accuracy of the U model over the I model suggests that the uniformly distributed prior probabilities may have been more helpful than the weakly informed prior distribution. Finally, the performance advantage of all these models over the random baseline model provides a good baseline measurement of success. The overall results demonstrates that the U, I, and FSM models performed much better than the RB model. The pairwise McNemar's test demonstrated that there was no statistically significant difference between the U, I, and FSM models. As depicted in the bar chart previously, both the CSF and FSM models have good prediction accuracies that is greater than 80% using only such simple linguistic status information. This in turn suggests that the linguistic information can be learned from data. Thus, to summarize our work, we presented the notion of a cognitive status filter, a statistical model for estimating the cognitive status of an entity that may be referenced in natural language. We then described a mechanical Turk experiment used to gather ground truth data to train this model. We showed that the overall accuracy of our CSF model in predicting the cognitive status of an object is as good as that achieved by a rule-based FSM model. This simultaneously speaks in favor of the heuristics encoded in the Givenness hierarchy coding protocol, while also demonstrating that those heuristics are learnable from data. However, there are a number of directions for future work that can improve the potential performance of the statistical cognitive status filter model over the rule-based FSM model. First, since our model worked on a relatively small corpus collected in a single task, our next step would be to collect a larger data set from a broader set of HRI scenarios, as that could yield a model with better generalizability. One of the theoretical advantages of the cognitive status filter model is its ability to handle uncertainty. The cognitive status filter model could straightforwardly be extended to include additional non-linguistic cues like gaze and gesture, which are inherently ambiguous and uncertain cues and critical in both human-human and human-robot communication. Similarly, we considered only 3 simple linguistic features given by the Givenness hierarchy coding protocol, whereas more complex and varied linguistic features could improve performance. So the main takeaways from this talk are, we developed and implemented a statistical model of cognitive status that seeks to predict the cognitive status of an entity based on whether and how it has been referenced in natural language. And we demonstrated that the accuracy of prediction of our statistical model is similar to that achieved by a theoretical finite state machine model. If you have any questions or would like to know more about our work, please feel free to reach out to me or visit our lab website. And thank you all for listening.